Well, good morning. I hope you all are more awake than I am. Can you hear me? Can you hear me now? All right, looks like I'm going to be standing here for a while.
Yeah, it's actually not on. I'll get just raise that one on.
Okay, how about now? Can you hear me now? All right, there's nothing like throwing the switch. I first became addicted to cold fusion while I was working at the Los Alamos National Laboratory. And during that, at that time, we were engaged in trying to put together a nuclear reactor that could be used in space to provide high electric power for communication and surveillance. And when Pons and Fleischmann made their announcement, everyone realized that if this were real and we could make it work, this would solve all our problems. And not only our problems, but all the problems of the world. It was quickly evident that this was a life-changing, economic-changing discovery. So the laboratory became incredibly excited. And that was back in the days when creativity was rewarded at Los Alamos. That's not so much now. But nevertheless, great enthusiasm. Meetings every week, bringing the staff up to date, large attendance at these briefings. And so it was really, really exciting to work there at that particular time. So I got the idea that maybe it might be fun to try to replicate this, and we set about doing that. Carol Talcott, who later became my wife, there was a reward in this work after all. So anyway, we set about trying to make tritium. And we did this because we were in a group that had the world's experts in tritium detection and tritium behavior. So we had a very good reservoir of knowledge about tritium. Carol was also an expert in the chemistry of palladium hydride and palladium deuteride. And I had a background in material science, which helped. So we set up in the lab to look for tritium, and we found it. And you can see in these two graphs, the one on the left shows the raw data from a number of cells that we're running. On the right, we see compared two cells that were running at the same time, at the same place. And this is with the corrections made, so it looks nicer. But the fraction increase, we essentially ran for 3 days, and then it suddenly started to make tritium. And the tritium in the deuterium oxide doubled. And then after about 25 days, it stopped making tritium. Well, this was pretty impressive because there's no possible way that tritium could be made other than by a nuclear reaction. So we showed this to the people in the laboratory up through the administration. And of course, that stimulated the creativity of the skeptics. I mean, there's nothing like the creativity of a skeptic to really awe you. They can think up all kinds of things. So they started to think up ways in which that could be explained other than the obvious. And each of their suggestions we took note of and paid attention to and did an experiment to show that particular explanation was wrong. So it wasn't a matter of ignoring them. We accepted everything they said, but that had no effect whatsoever. So this was eventually published in the open literature in fusion technology. And then the skeptics said, well, we can't trust these publications because they're not peer-reviewed. they're not suitably criticized. This paper was probably the most peer-reviewed, criticized of any paper published by Los Alamos ever in the history of mankind. I mean, it was thoroughly reviewed, picked apart, and then when it got to the journal, another set of reviewers took over, and it was eventually published. Well, that still had no effect. Well, meanwhile, other people were seeing tritium as well. In fact, is at Los Alamos, Tom Claytor, who is at this conference, was able to make tritium by a gas discharge technique, which he continued to explore with support for many years and is continuing to explore now in his own laboratory. Well, I should talk about John Bockris a little bit, because we and John, in his mind, were in a race to be the first to make tritium. And only later did we realize that he had an unfair advantage. So in our case, we used sealed cells, and no water or any light hydrogen could get into our cell. We thought this was really important. On the other hand, John created cells that were open, and the water from the atmosphere got in, and he even analyzed the amount that was in there. So we know that these things were taking up light hydrogen. Only now do we know that you have to have light hydrogen with heavy hydrogen to make tritium. We didn't know that at the time, and of course, John benefited from sloppy experimental design, which frequently happens in this field, it turns out. So anyway, but John won the race. And then the ERAD panel met and resulted in, as I say, disappointment, anger, disgust, depression, and distrust. Garwin came and sat in my office and heard my whole story, went away, and paid no attention to it. Teller asked me to brief him, and I spent an hour with him telling him all about it, and he went away and paid no attention to it. So the ERAD panel essentially ignored all of the information that was being accumulated, and it essentially shut down all work in the national laboratories as well as elsewhere in many cases. So that didn't stop us. Back in those days, before the bureaucrats had the ability to look deep into the organization, you could do things under the radar. You could run experiments that the bureaucracy didn't really know about. So the cold fusion went underground in my case, and also Tom Claytor. And we worked on it quite a while because our group leaders, the people local who made decisions at that level, knew this was real, knew that it was important. And that was probably true at higher levels, but they had to follow the rules of the DOE. Well, meanwhile, I set about writing reviews. And up till now, I've written a dozen of them, and you can see them there. They're published in readily available journals, in addition to 2 books. Both books are no longer in print, but you can obtain electronic copies. The first book, you can obtain an electronic copy from World Scientific, go to their website, and the second book, you can get it from Amazon as a Kindle edition. Well, after I had written the first review, that was persuasive, sufficiently persuasive to my division leader for him to find some money to build a calorimeter. And when they found out, the bureaucrats found out later on what it was used for, he paid a price, but the calorimeter was done and we were making measurements. So from my point of view, this worked out pretty well. But I was lucky, and I got a piece of palladium from Takahashi in Japan. He had a sheet of palladium made that he was finding made excess energy fairly routinely. So he sent pieces of it around to various laboratories throughout the world, and they all saw the excess energy, and he sent a piece to me. And so that was the first sample I ran in my calorimeter, and because it produced some significant energy, I was hooked. And I'll show you the implications of his contribution a little later. But meanwhile, having retired, I set about building a house. My wife and I set about building a house in Santa Fe. And I was the architect, contractor, plumber, electrician. I mean, we did this pretty much ourselves, hired a crew, hired SEBs when we needed them. But this was pretty much a creation of our own hands and our own imagination. And you see two views, one from the laboratory towards the main house and the other towards the laboratory from the main house. I show the snow scene there because of the drought. That is increasingly rare, and it's really nice to be reminded that it can snow at that part. The design of the house was very simple. My wife said that the kitchen is going to have the view, or you're never going to have another meal. So she got the view. The house is solar heated. We have a solar electric, so our electricity all comes from the sun. We have a plug-in hybrid, so that's all comes from the sun. So we're doing our best to save the world in anticipation of cold fusion coming along someday and taking over from these other efforts. I had an interesting experience. We were working on the house, got a call from Los Alamos, and they said, well, we want you to testify before Congress. And it turns out that Congressman Sweat, who is a congressman from New Hampshire, or was at that time, and a friend of Gene Malov, was convinced that cold fusion was real. And he was a member of a committee that was evaluating the hot fusion program. So he wanted somebody there to sort of stick it to the hot fusion people to show that there were other possibilities. And these guys were not the only game in town. And I was to be one of the players in this drama. But so he went to the lab and said, I want Storms to testify. And the lab said, no, we don't do that. You know, we have people that know how to behave in front of Congress, so we're not going to let Storms do that. Well, congressmen have a tremendous amount of persuasive ability. And so I was taught how to behave in front of Congress by the experts, and then shipped off to Washington, where I participated in this little drama that he had set up. When I got there, I discovered that there were two other members who were there to do the same thing. One was Randy Mills. He was showing them how they can make heat by his technique. And then there was a fellow that I hadn't heard of before who had a better design for the hot fusion reactor. And so they listened to the hot fusion people, and then they listened to us. I had the opportunity to put a lot into the congressional record. And also, unfortunately, the lab would not stand behind anything I said. I could write and say whatever I wanted to, but I had to make it very clear that those were my personal opinions. The lab had nothing to do with it. And all right, that was okay. So all this was done. The budget was approved. Hot fusion proceeded onward. Cold fusion was ignored, and nothing changed. But it was really a delightful experience. I was involved with a company called ENECO. ENECO was created by Charlie Becker, as well as a number of other investors, for the purpose of acquiring the patent to the Pons-Fleischmann method, and then leasing it to industry, and thereby making money. So Charles Becker asked me to be his eyes and ears, and also from a scientific point of view, I was given a seat on the board of directors. And my job was to put together the scientific facts in a form that could be sent to the patent office and that would persuade an objective, intelligent person that cold fusion was real. Well, we would send off a package of information to the patent office, and then we'd get back a rejection, and the explanation for the rejection was that there was an article in the New York Times that said that this was not real, and that's all that mattered. And we kept doing this for a year, and finally it became clear that the only way of overcoming this was suing the patent office, and that would have taken too much effort. So that effort essentially terminated, and the laboratory was focused now on trying to create a better thermoelectric converter. Unfortunately, that effort also failed, and then eventually the company went bankrupt, and Charles Becker lost about $6 million. He still is interested in cold fusion. You can see what it does to you. I mean, it is true, it's a true addiction. Well, once I had the house built and the laboratory created, one of the early experiments was an effort to try to replicate the Dennis Letts single laser claim. He claimed that if you shone a red laser onto a palladium cathode while it was being electrolyzed, you could stimulate greater energy production. And so Mike also at SRI was given a chance to replicate that and was successful. I worked with Dennis, he supplied the lasers, and I applied it according to his recipe and found it to be successful. But then I went several steps further. I did not put down the gold coating that he required. I did not apply a magnetic field. I did not treat the surface in the way he prescribed, and it still worked. And in addition, with the early calorimeters, you could only see a change. You did not know whether there was an absolute amount of power. But I got a commercial CBEC, which allowed me to measure absolute power very accurately, and it turned out that the cells or the materials that worked were materials that already would produce a small amount of LENR energy, and the laser simply amplified that so that it increased above the sensitivity level of the calorimeter. And therefore it looks like it turned on when in fact all you were doing was amplifying something that was already happening. And I won't go, that's the data, but that's too much detail. I want to talk about this particular phenomena that I alluded to in my talk on Wednesday. And this is really, really important. When palladium is loaded with hydrogen or deuterium, it expands. And it expands in a way that's consistent with the lattice parameter. Now, on the graph on the left, you'll notice that's the volume fraction increase, that is the physical volume, against the atom ratio. And you'll notice the points are following the dashed line, which is what you would expect based upon the lattice parameter change. But once you get within the beta phase, the expansion accelerates. It goes above the line that you would expect based upon lattice parameter. That excess I call excess volume. The magnitude of that excess is characteristic of the material. It is, some materials have a small amount and some materials have a large amount, and we'll see the consequence of that very shortly. Now, the interesting thing is that if you, and I'm going to have to use a pointer here for this, I think. If you went up here and went back down, of course, you go back down and that's retained. That's a permanent change. But if you go back up again, once you get to this composition, it'll increase by that same amount, and then you'll go back down again, and you'll just simply keep adding volume. Now, that volume manifests itself in a very strange way. The length and the width shrink, and the thickness increases. And you can use the thickness increase as a diagnostic, and this is the thickness increase as a function of number of times that this has been cycled. And you'll see that it's a straight line, and it'll just continue on up. And in fact, if you do this often enough, a sheet will turn into a cube. And this is a permanent change with extra volume within the structure in manifesting itself in very strange ways. So loading and deloading is important, but if you do it, you are changing the nature of the sample, and you need to take that into account. Well, IMRA in Japan sent me a collection of 90 samples of palladium treated 8 different ways. And they did this for me to measure the excess volume and relate it to the ability to make excess energy. Here's an example of the relationship between excess volume and the ratio, the D to PD ratio. And you notice that samples that have a high excess volume do not load well. Samples that have a low excess volume do tend to load well. There's a lot of scatter, so there's obviously other variables operating, but nevertheless, there is a very clear trend that operates there. So what you want to do if you want to get the high compositions is to find a material that has the characteristic of producing a very small amount of excess volume. Well, how does that relate to the excess energy? Well, if we take Tanaka 1, that's the first sample that Takahashi sent me. I measured the excess volume, 1.7%, quite low. Composition 1.82. I got 7.5 watts of excess power. And these are all at the same current and therefore roughly the same temperature so that they can be compared. He then, after that stopped working, he had another batch made called Tanaka 2. Sent that to me. It had 13.5% excess volume. Quite different. Only went up to 0.75 and produced no excess energy. Well, that was a surprise because he had told the company to do it exactly the same way as the first one, but they obviously had not. So they were given another chance, and that produced Tanaka 3. That produced 2%. Okay, that's back down in the category of the first one. 0.84, that's good. And it produced 2 watts. Not too shabby, but nevertheless not as good as the first one. So it was very clear to us that the excess volume played a role, that the absence of excess volume played a role in being able to support the cold fusion reaction. And that same trend was manifested in the IMRA samples. Those were all measured and also gave excess energy, and the excess volume followed, and the excess energy and the excess volume followed that same trend. So that's an important diagnostic. I mean, and why one sample of palladium would produce large excess volume and others would produce low excess volume, I have no idea. But something about the way they're manufactured and treated affects it that way, and that behavior affects whether or not you can make excess power. So we can look at it either way. I mean, you can pre-diagnose whether this material is going to work simply by its loading characteristics. Well, then my work started getting attention by people who had money. Louis Larsen funded me, made me a part of his organization, Lattice Energy. He provided money to construct a number of Seebeck calorimeters of my own design that turned out to be far better than anything I could buy, and certainly a very excellent way of doing calorimetry. He also bought an SEM with EDX. And I might point out, I like to brag a little, I'm the only person in my neighborhood who has an SEM. So, I mean, I'm really proud of that. Maybe even the only person in Santa Fe. So, anyway, he funded studies using different kinds of palladium with different coatings. But we never solved the problem. We never were able to reproduce or amplify the effect to the level that he expected, and so eventually he said, "The heck with it," and he went his merry way. Brian Scanlan then supported me. Brian's really an interesting guy. He made his money in software, but he always wanted to be a physicist. And now that he had the money, he could become a physicist. So he created a laboratory in the basement of his pool house. It's the only pool house in Greenwich, Connecticut. It's a disguised cold fusion laboratory, actually, and it's really very, very strange. But anyway, we worked together very nicely. He had a theory of how this could work, and so we worked on that. But one of the experiments we did that he funded was exploring the gas discharge, looking for radiation produced by the discharge. And that was truly extraordinary. And you can see the discharge is here. That's the anode, and the cathode is within this shroud of aluminum oxide. And so the discharge takes place right in there. And then whatever ions are produced, or whatever atoms are ejected, they are detected by both a Geiger counter and a silicon barrier detector. So I can determine the energy and the characteristics. And that is done because I have the ability to impose various absorbers between the detector and the source, and the way in which those absorbers change the energy and the intensity can reveal the nature of the radiation. The nature of the radiation turned out to be absolutely extraordinary. First of all, we did see photons, fairly low energy, but not strong enough to get out of the apparatus. But we also saw this behavior. These were identified as energetic deuterons. And they come off this is a spectrum of energy versus intensity. And the ones that have the least intensity, or the least energy, have the maximum intensity. And you can see it drops down. Now, these things are very, very energetic. I mean, we're talking about MeV. These can only originate from a nuclear reaction. So these are coming out of some kind of nuclear reaction that's taking place on the surface, but they're coming out with this rather strange characteristic. I could never make sense of it. So I was loath to publish it very widely, but maybe some of you have the imagination to figure out what this means. And I'll be happy to share the information with you if you can do that. Because this is truly unusual and very novel, and no doubt reveals something very, very important about the nuclear reaction. Well, Brian and I then set about trying to reproduce the Rossi claim. And we came to the conclusion that Rossi did not use nickel. We tried exploring all kinds of nickel, including the one that he claimed to use, and none of them produced anything. And in fact, there was no evidence that they could produce anything. What I believe is that Rossi actually used a commercial catalyst because he was trying to initiate a reaction between gases to make a liquid fuel. You would not have used solid nickel for that purpose. You would have used a nickel catalyst. So I went to the literature and I looked up the kind of catalyst that you would apply for that particular reaction, and that's known. And I tried to order some, and it sold out. Now that's maybe coincidental, or maybe he just simply bought out all the available catalysts, so it's not available to anybody else. Anyway, Rossi is a strange phenomena, but you have to be incredibly careful in believing and analyzing what he says, because some of it is true and some of it is not true. My present studies are designed around a calorimeter that I built recently that I showed its characteristics on Wednesday. This gives an overview of what it looks like. It turns out to be a very effective calorimeter. I would highly recommend it. It is probably the ideal calorimeter for doing work in cold fusion. And if you are interested in making one, please let me know and I can give you all the details. Well, I see my time is up, and I respect the clock, and so you can ask any question you want.
It was a very interesting historical account. I had just two remarks. One was regarding the dispute you had with Bockris on who got tritium first. And we went and I had a long conversation with Bockris, and I'm happy to say that I have an email from Bockris a year before he passed away, that, okay, Chino, I agree, you were the first to publish it. We published tritium production in July 1989 at a meeting in Karlsruhe. But Bockris still said, oh, but we were the first to observe it. You might have published it first. But however, this was just a few months before it. The second remark was, in this whole business of tritium production, if you remember in the good old days, we used to talk about the neutron to tritium, the so-called branching ratio anomaly. And what is the correlation between the production of neutrons and tritium? In our observations, we were in many of the cells, we were measuring neutron bursts and also taking samples of the tritium, the electrolyte, every few days or hours. And invariably we found that the tritium level went up whenever there was a big burst of neutrons. And therefore, I'm convinced there's some correlation, but I don't understand. I agree with you, the tritium reaction is probably hydrogen and deuterium, but that puzzle remains. Later, this so-called branching ratio anomaly was confirmed by Bockris, confirmed by somebody from Taiwan, and I think even Tom Claytor. So I haven't understood. Nobody talks of neutrons these days, but there is a very interesting something there. Thank you.
The ratio, the tritium to neutron ratio, has been reproduced now, measured numerous times. And if you plot a histogram of the number of occasions against the ratio of tritium to neutron, there is essentially a greater population at a ratio of about 1,000,000 to 1. And so there is, in fact, obviously a correlation between the two, so they are possibly originating from a similar reaction, but it's much different than occurs from hot fusion.
Thank you very much, Ed. In the interest of getting people out of here on time, I'm going to close this down. I would like to say one thing, though. Your powers of persuasion are greater than you think. When Gawain came to your office, you didn't convince him because he already knew it was true.
Oh.
And you convinced Teller. Teller was supportive in the background for the rest of his life.
Well, I appreciate that. Unfortunately, it didn't have any long-term effect, but that's okay.
Right.